And of course, when you have structures and when you're thinking in 3 dimensions, you can have isomers. And of course, if you remember, isomers are compounds that have the same formula but different structures. Now, as was the case with organic chemistry, we can split our isomers up into structural isomers. These are species, the same formula, but different connectivity. So often very different compounds. And then, of course, we have as well as structural isomers, so-called stereoisomers. These have the same connectivity, different 3-dimensional arrangement. Structural isomers, we split them into 4 distinct types. I know at A level with structural isomers, you talk about chain and group isomers. I don't feel you really need to do that to get a feel for what structural isomers are. But however, the different types of structural isomers and coordination compounds are very, very different from each other, as we'll see over the course of the next few slides. But you can have coordination isomers, ionization isomers, and hydrate isomers, really different sides of the same coin. And then linkage isomers, something that's really cool and fascinating and you don't find in organic chemistry. Now, within stereoisomers, same connectivity, different 3-dimensional arrangement, you are used to 2 types in organic chemistry, geometric isomers and enantiomers, and we see those same things here. Geometric isomers like the cis-trans, the EZ isomers that you've seen before, and enantiomers, of course, when you have a carbon with 4 different groups around it, leads to having mirror images that are non-superimposable. Anyway, we're going to look at these 6 types of isomers for coordination compounds. Starting off with coordination isomers. Coordination isomers are simply where you're switching ligands between 2 complex ions in the same compound. They're fun, they're cute, there's not a whole lot of them, they're not overly interesting. But for example, if we look at this species here where we have a complex cation, so a zinc bonded to 4 ammonias, a complex anion, copper bonded to 4 chlorines. So we would have the cation zinc with 4 ammonias, that's zinc 2+, because of course ammonia is neutral and zinc only ever makes 2+. Copper can be copper 1 or copper 2, but in this case the zinc tells us that the cation is 2+, so this must be a 2- anion. You've got 4 chlorides, each of which is -1, so the copper must be +2. Okay, now the coordination isomer of this could be the species up here, where now instead of the ammonias being bonded to the zinc, they're bonded to the copper, and instead of chlorides being bonded to the copper, they're bonded to the zinc. You still have between both of these, and let's just fill everything out, you still have a zinc and a copper, you still have 4 ammonias, you still have 4 chlorides, but they are bonded to different metals. Just quickly pointing out the naming of this, we'll always write the cation and the anion. So here the zinc has got 4 ammonias around it, so that's tetraamine, and it's zinc. It's sort of redundant to put the 2 here because you're never going to see zinc as anything other than 2+ or 0, but we'll be good and we'll put it there. And then of course with the anion here, we've got 4 chlorides, that's tetrachloro, copper, but as it's an anion, it's not copper, it's cuprate. And then of course we already said it's copper 2+, and then switching around here, so the cation has got the 4 ammoniums, so tetraamine on the copper, but now it's copper 2 instead of cuprate 2 because it is in the cation rather than the anion. And then over here tetrachloro, but now zincate 2 because now that zinc is in an anion. Okay, so coordination isomers were essentially you're swapping ligands between 2 different metal centers in the same compound. Moving to ionization isomers here. This is where you have a swap between coordinated and non-coordinated ligands, or I would say primary and second coordination sphere. So if we look at these 2 compounds here, our first one, we got a cobalt that has 5 waters, so penta-aqua, and a bromide around it. The whole cation is plus, well, only bromide is the anionic species there, so 5 neutral waters, 1 minus for the bromine, so the cobalt must be 2. And then the nitrite anion is outside, so water, bromide, primary coordination sphere, nitrite. Second coordination sphere, compare it to this compound over here. Again, we have 5 waters, but now the nitrite is coordinated, so it becomes nitrito, and the bromide is outside in the secondary coordination sphere, so it's bromide. Again, same formulas. You've got a cobalt, you've got 5 waters, you have a nitrite, and you have a bromide, okay, but different structures, different coordinated versus non-coordinated ligands. You've switched over the ions, essentially. One ligand that is anionic goes from being coordinated to outside to being an anion, and the other original anion is now coordinated there. Probably made a bit of a meal of that description, but that's an example of ionization isomers, in which you're swapping over anionic ligands for an anion. Hydrate isomer, very much the same thing, except now instead of switching anions, you switch water ligands. So this is a very famous little series here. We start off with a chromium with 6 waters around it. It's chromium 3+, so you've got 3 chlorides as the anion, so it's hexaquochromium 3, and then chloride. Tri is not actually needed, although you'll see some people putting it there because the tri is defined by what the cation is. Now let's switch one of those waters for a chloride. Okay, so now the cation is no longer 3+, it's 2+, because we got an anionic ligand in there. One of the waters has gone to the secondary coordination sphere, so this is going to be pentaquochlorium chromium 3 chloride, and then you say the hydrate because that is a water that is associated with the whole species. It's in the secondary coordination sphere, and then we can do another one. So we get this species here in which now we have 2 chlorides on there, 1 outside, so only tetraaqua now, dichloro, still chromium 3, but now the cation is only +1 because we got 2 anionic ligands, and then you got a chloride out there, and you got 2 waters, and here of course you do have to say dihydrate because you can't possibly figure out how many waters there are in there from the rest of the species. So hydrate and ionization isomers, essentially switching between the primary and the secondary coordination sphere. Sometimes your solvent's not going to be water. You can still get this going on if your solvent is a coordinating solvent. So water hydrate isomers, actually a special case of so-called solvate isomers. Last type of a structural isomer, linkage isomers. This is where you have a ligand that has more than one donor atom, a so-called ambidentate ligand, right? It's not bidentate because it's not got 2 coordinating atoms that are going to coordinate to the same metal atom, but it has 2 atoms that could coordinate. We actually saw this earlier when I was going through types of ligand with the thiocyanate. You can coordinate through the nitrogen or through the sulfur. Another fun one that has great historical importance is nitrite. You've already seen that. Nitrite, NO2-, it's got a nitrogen with a lone pair and of course oxygens with a lone pair. Way back in the first early days of coordination chemistry, there was 2 compounds discovered by a chap called Alfred Werner that had exactly the same formula. One was yellow, one was red. The yellow one was later determined, actually he had a pretty good idea of it, but it was later demonstrated, is where you have the 5 ammonias obviously coordinated to the cobalt, the nitrite coordinated through the nitrogen atom. The red isomer is again, you've got the same 5 ammonias coordinated to the cobalt, but now the nitrite is coordinated through an oxygen. So you change not the ligand, but which atom it is coordinated through. Now naming this gets kind of fun. Okay, there's various ways you can name it. Obviously we've got the pentyramine, we've got cobalt 3. Okay, it's cobalt 3 of course. Ammonia is neutral, nitrite is 1-, so therefore if the whole cation is 2+, the cobalt must be +3. So we can name it this way, in which we say, well, it's nitrito, that's the ligand nitrite, in which you have this kappa N, it's bonding through the nitrogen. Alternatively, it should be pentyramine nitrito, kappa O. Okay, again, cobalt 3 the same. So use the kappa to say which atom it's coordinated through. You can Change the name of the ligand. When it's coordinated through nitrogen, you call it nitro. When it's coordinated through the oxygen, you can call it nitrito. We can demonstrate it in the formulas in two ways. We can write it like this and say it was cobalt nitrate coordinated through the nitrogen. Rather confusing because it implies there's another nitrogen there. No, this is saying coordinated through the nitrogen or coordinated through the oxygen. Or we can write the formula that expresses that coordination. So here the cobalt onto the nitrogen, which has a couple of oxygens on it. Or here's the cobalt onto the oxygen, which has a nitrogen and an oxygen on it. Anyway, linkage isomers, I think, are the coolest type. Significance, amazing the difference you can have in, for example, the color just by switching out nothing except which atom an ambidentate ligand coordinates through. And we'll encounter this again when we start coming back to that thiocyanate, whether it coordinates through the nitrogen or coordinates through the sulfur. Fun stuff.